This sheet of paper, or the screen you are holding, is about 1 million atoms thick. Not roughly, that is the count. A human hair is another million across, a grain of sand a few tens of millions, and every dimension of every object you have ever picked up is a number of atoms multiplied by the width of 1. For hydrogen, that width is 5.29 times 10 to the minus 11 meters, and it is very nearly the same for uranium, which carries 92 times the charge and 238 times the mass. But here is what that leaves out. Under the laws of electricity alone, an atom should have no width at all. The electron should fall into the proton, releasing an unlimited amount of energy in about 16 trillionths of a second, and every atom in the universe should have vanished that long after it formed. Something stopped it, and whatever stopped it did not just prevent a collapse, it fixed a specific number to 11 decimal places, everywhere, forever. So what determines the size of atoms, and why that number and not another one? Get comfortable, hit subscribe if you're new here, because by the end of this, you will know exactly why matter has any volume at all, and why the hardness of the floor beneath you is not the thing you were told it was. Now, let's slowly ease into this. Part 1. The thing that has a size. There is a sheet of paper somewhere near you. If you were to measure its thickness, not with a ruler, but by counting, you would find that it is about 1 million atoms thick. Not a figure of speech. 1 million, stacked one on top of the other, from one face of the page to the other. And the reason a page is as thin as it is, and not thinner, is that you cannot stack fewer than 1 million atoms and still have a page. The atoms have a size, the page inherits it. This is true of everything. The width of a human hair is about 1 million atoms. A grain of sand is a few tens of millions across. The distance from your fingertip to your shoulder is somewhere around 10 billion atoms laid end to end. Every dimension of every object you have ever picked up, leaned against, or fallen asleep on is, at bottom, a count of atoms multiplied by the width of one atom. Change the width of one atom and you change the size of the world. So what is that width? For hydrogen, the simplest atom there is, the answer is about 5.29 times 10 to the minus 11 meters. Written out, that is 0.000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 and it has a name, measured to 11 decimal places, and it has a name, the Bohr radius, and physicists write it as a little letter A with a 0 after it. And here is the first strange thing, the one that almost nobody stops on. Hydrogen has 1 proton and 1 electron. It is the least of all possible atoms. Uranium, sitting at the heavy end of the periodic table, has 92 protons and 92 electrons, 92 times as many charges, 238 times the mass. You would expect it to be enormously bigger. It is not. It is roughly the same size, a little larger by some measures, a little smaller by others, but the same order of magnitude, the same neighborhood of about 1/10 of a nanometer. In fact, almost the entire periodic table lives inside a single narrow band. From hydrogen at the light end to cesium, which is the biggest stable neutral atom there is, the whole range spans less than a factor of 10, 118 different elements, made of wildly different numbers of particles, held together by wildly different amounts of charge, and they are all, every one of them, about the same size. Something is enforcing that. Something is holding all of them to the same standard. And there is a second thing, stranger than the first, which is that under the physics that was known for the entire 19th century, none of them should have any size at all. Not a large size, not a small size, no size. Because the atom, described by the rules of electricity alone, should collapse. That is the story tonight. Not the collapse. That is only the beginning of it. The story is what stops the collapse, and how the thing that stops it also, in the same motion, sets a specific number, and how that number turns out to be exactly the width of everything. By the end of this, you will know exactly what determines the size of atoms. You will know the two forces that fight over it. You will know the equation that settles the fight, and you will know why the settlement lands where it does. You will also know something that most people who have taken a physics class never quite absorbed, which is that an atom does not actually have an edge, and that the number I just gave you, the 5.29, is not a measurement of a boundary, but a description of a compromise. Let me put the question as plainly as I can before we start pulling it apart, because I want you to feel it as a question and not just hear it as a topic. Take a hydrogen atom. It is one proton and one electron. The proton carries a positive charge. The electron carries a negative charge of exactly the same size. Opposite charges attract. There is nothing else in the picture. No third particle holding them apart. No rod, no spring, no wall. So what, exactly, is keeping them separated by 5.29 times 10 to the minus 11 meters? Nothing you can point to. There is no mechanism in that picture. And yet the separation is not only stable, it is precise. Every hydrogen atom in the universe agrees on it. The hydrogen in the water you drank this morning and the hydrogen in a gas cloud 11 billion light-years away are exactly the same size, to a precision better than anything humans can manufacture. Whatever sets the number, it is not local, it is not negotiable, and it does not drift. We are going to build the answer slowly. We will start with the problem, because the problem is much worse than most people realize, and it is worth letting it get genuinely bad before we fix it. Then we will bring in the piece of physics that fixes it, and it will be a piece of physics you have almost certainly heard of, and almost certainly heard described wrongly. Then we will do the arithmetic, twice, by two completely different routes, and watch them arrive at the same address. And then, near the end, we will find that the answer has a hole in it, a very small hole, in the shape of a number that nobody can explain. There is one more thing I want to plant before we go. Hold on to the figure, 5.29. It is going to disappear for a while. We will spend a long stretch of tonight in territory where no numbers show up at all. And then it is going to come back, unannounced, out of an argument that looks nothing like where we started. And when it does, I want you to recognize it. For now, though, we have to go backwards. Because before anyone could ask why an atom is the size it is, somebody first had to notice that it should not be any size at all. Part 2. The funnel with no bottom. Let us build the problem carefully, using nothing but the physics of electric charge, which was understood completely and confidently well before anyone knew that atoms had parts. If you have two particles carrying electric charge, and you separate them by some distance, the pair of them together stores a certain amount of energy. Physicists call it potential energy, and the word potential is doing exactly the work you would expect. It is energy that is available, energy that could be released, energy waiting in the arrangement rather than in the motion. For two charges, the rule is simple, and it has been known since the 1780s. The potential energy is proportional to the product of the two charges, divided by the distance between them. Multiply the charges together, divide by the separation, multiply by a constant that sets the units, and you have it. That is the whole law. Now put in the specific case we care about. Particle 1 is a proton. It carries the fundamental unit of positive charge. Particle 2 is an electron. It carries exactly the same amount of charge, but negative. Multiply a positive by a negative, and you get a negative. So the potential energy of a proton and an electron, separated by some distance, is a negative quantity divided by that distance. That minus sign is the entire problem, so let us sit with it for a moment. A negative potential energy means the two particles are bound. It means that if you wanted to pull them apart, you would have to do work. You would have to supply energy from outside. That is what attraction means in the language of energy. Opposite charges attract. A proton and an electron attract. The arrangement is bound. But look at what happens to that number as the distance shrinks. The energy is negative, and it is divided by the separation. Make the separation smaller, and you are dividing a negative number by a smaller and smaller quantity, which makes the result more and more negative. Halve the distance, and you double the negative energy. Halve it again, and you double it again. There is no limit to this. As the separation goes to zero, the potential energy runs off toward negative infinity. If you draw this, and I want you to draw it in your head because we are going to come back to this picture repeatedly tonight, it looks like a funnel. Put the distance between the proton and the electron along the horizontal axis, and put the energy on the vertical axis. Far away on the right, the energy is very close to zero. Two particles far apart barely know about each other. As you move left, towards smaller separations, the curve dips below zero and then plunges, faster and faster, diving toward the bottom of the page and never coming back up. In 2 dimensions, you can imagine it as a well in a surface, a smooth, steep-sided funnel with the proton at the center and the walls getting steeper the closer you get. And the electron is a marble somewhere on that surface. Here is the principle that turns this picture into a crisis. Physical systems, left alone, move toward lower energy. Water runs downhill. A stretched spring relaxes. A hot object cools. A ball on a curved surface rolls toward the bottom. This is not a fringe idea in physics. It is close to being the organizing principle of the entire subject. If a system can lower its energy, it generally will, and it will keep doing so until it cannot lower it any further. So look at the funnel again and ask the obvious question: where is the bottom? There is no bottom. The curve does not level out. It does not reach a minimum and turn around. It descends without limit, and every step the electron takes toward the proton releases energy and puts the system in a lower state than before. There is no configuration where the electron can be that is not improved, energetically, by moving a little closer. Which means that under this law, the only law we have used so far, and a law which is completely correct, by the way, and has never been overturned, the electron should fall into the proton. It should keep falling, releasing more and more energy, until the separation is zero and the energy is negatively infinite. The atom should have no size. The atom should be a point. And it is not just hydrogen. Every atom in the universe is built from positive charges in the middle and negative charges outside, and every one of them is described by the same funnel. So the prediction is not that one particular atom is unstable. The prediction is that matter, as a category, is impossible. There should be no chemistry, no molecules, no solids, no liquids, nothing with volume. There should be a fog of collapsed point-like objects, and nothing else, anywhere, ever. There is a way of feeling how bad this is that does not require any equations, and it comes from asking what the collapse would actually release. Every step the electron takes toward the proton, the arrangement gives up energy, and that energy has to go somewhere, as light, as heat, as radiation flung out into the world. And because the funnel has no bottom, the amount of energy available is not merely large, it is unlimited. A single hydrogen atom, allowed to complete the classical collapse, would emit an infinite quantity of energy on the way down. That is a useful kind of absurdity, because it tells you something has gone wrong structurally rather than numerically. Physics has a long history of theories that give answers which are too big, and almost every time, the infinity is a signal that the theory has been pushed past the domain where it applies. Newton's mechanics gives nonsense at speeds near the speed of light. Classical electromagnetism gives nonsense for the energy radiated by a hot object at short wavelengths. That was the ultraviolet catastrophe, and it was the crisis that gave birth to quantum theory in the first place. Here, the same warning light comes on. An infinity means the map has run out. And notice that the infinity arrives for a very specific reason, because the theory permits the separation to become arbitrarily small. If something forbade the separation from shrinking below some scale, the energy would be finite and the world would be safe. So the shape of the missing physics is already visible in the shape of the failure. Whatever we are missing does not need to be a new force. It needs, somehow, to make very small separations impossible, or at least unaffordable. I want to be very clear that this is not a straw man or a historical curiosity dressed up for drama. This is a straightforward, unavoidable consequence of taking the law of electrostatics seriously and applying it to a proton and an electron. Nobody has ever found an error in the electrostatics. The law is right, the funnel is real, the energy really does run off to negative infinity as the separation goes to zero. Something else has to be in the picture, something that we have not written down yet. And notice what kind of thing it has to be, because this is going to constrain the answer enormously. Whatever stops the collapse cannot be another attraction. That would only make things worse. It has to push back. It has to oppose the shrinking, and it cannot be a weak effect that only shows up under special conditions, because the atom is stable always, everywhere, for every element, at every temperature we have ever tested. Whatever it is always on. More than that, it has to get stronger as the atom gets smaller, because the funnel gets steeper as you approach the center. If the opposing effect stayed the same strength, while the funnel deepened, the funnel would eventually win, and the collapse would resume, just delayed. To hold the line at a fixed distance, the counterweight must grow faster than the funnel does. It must, in some sense, become infinitely stubborn at short range. That is a demanding specification. It is not obvious what physical effect could possibly satisfy it. Nothing in classical mechanics does. Nothing in electromagnetism does. Nothing in thermodynamics does. And there is worse news coming, because the funnel, bad as it is only the first of the two ways in which classical physics predicts the atom cannot exist. The second one is more specific, more violent, and it comes with a number attached, a number that tells you exactly how long the universe should have lasted. Part 3. 16 picoseconds. In 1911, in a laboratory in Manchester, Ernest Rutherford was firing alpha particles at a sheet of gold foil so thin it was semi-transparent. The expectation was that they would pass straight through with only slight deflections, because the accepted model of the atom at the time was a diffuse smear of positive charge with electrons distributed through it, soft, spread out, nothing hard enough to bounce anything. Most of them did pass straight through, but a very small fraction, roughly 1 in 8,000, came back. Not deflected slightly, reversed. Rutherford's remark about it has been quoted so often it has worn smooth, but it is still the best description anyone has given. It was as if you had fired a 15-inch shell at a piece of tissue paper and it had come back and hit you. The only arrangement that could do that was a nucleus, a tiny, dense, positively charged core, holding essentially all the mass of the atom in a volume vastly smaller than the atom itself. The numbers that came out of it are still hard to hold in the mind. The nucleus of a hydrogen atom is about 100,000 times smaller than the atom. By volume, that is a factor of 1,000 million million. If you scaled a hydrogen atom up to the size of a large sports stadium, the proton at its center would be about the size of a grain of rice on the center spot. So Rutherford had established the geometry, a hard point in the middle and the electron out at the edge. And the moment he established it, the stability problem became acute in a new way, because now you had to say what the electron was doing out there. The obvious answer was that it orbits. It is the same geometry as a planet around a star, with the same inverse square attraction, and the mathematics of orbits was 200 years old, and completely trustworthy. A planet does not fall into the sun because it is moving sideways fast enough that its fall keeps missing. Why not say the same about the electron? Because of a fact about electric charge that Rutherford's contemporaries knew perfectly well and could not get around. An accelerating electric charge radiates. It emits electromagnetic waves and loses energy in the process. This is not a subtle prediction. It is the operating principle of every radio transmitter that has ever been built. You take electrons, you shake them up and down in an antenna, and because they are accelerating, they broadcast energy into space as radio waves. The relationship is quantitative, and it has a name, the Larmor formula, and it says that the power radiated is proportional to the square of the acceleration. Now, an electron in a circular orbit is accelerating constantly. This trips people up, because in everyday speech, acceleration means speeding up. In physics, it means any change in velocity, and velocity includes direction. A body moving in a circle at perfectly constant speed is accelerating the entire time, because its direction is changing the entire time. That is what it means to turn. So the orbiting electron is permanently accelerating, and therefore permanently radiating, and therefore permanently losing energy. And an orbiting body that loses energy does not slow down and stay put. It spirals inward. You can calculate how long that takes. It is an undergraduate exercise, and it has been for a century. Take a hydrogen atom at the size we actually measure. Apply the Larmor formula. Let the electron radiate away its energy, and integrate to find when the spiral reaches the nucleus. The answer is about 1.6 times 10 to the minus 11 seconds. 16 trillionths of a second. 16 picoseconds. Let me try to give you a feel for how short that is, because the number is so far outside human experience that it just reads as small. Light, the fastest thing there is, travels about 5 millimeters in 16 picoseconds, less than the width of your fingernail. In the time it takes light to cross your thumbnail, according to classical physics, every atom in the universe should have collapsed. This is the point I want to leave you with, and it is worth stating without softening it. The physics of 1911, the physics of Maxwell and Newton, the most successful, most thoroughly tested, most triumphant body of theory that human beings had ever assembled, predicted that matter could not exist for longer than a few trillionths of a second. Not that matter was fragile, not that atoms were hard to explain, that the entire material universe should have ceased to be, essentially instantaneously, at whatever moment it first came into being. And of course it did not. That is the peculiar thing about this crisis. It was not discovered by an experiment that produced an unexpected result. It was discovered by looking around. The refutation of the theory was the existence of the person doing the theorizing. It is worth pausing on how the physicists of the period actually experienced this, because it was not the calm intellectual puzzle that textbooks imply. The Larmor result was not controversial. Nobody doubted it. It was being used, at that exact moment, to design the antennas that were carrying radio traffic across the Atlantic. There was no wiggle room in it, and no serious hope that a more careful calculation would make the spiral go away. So the situation was that the two most secure bodies of theory in existence, Newtonian mechanics and Maxwell's electromagnetism, which between them had explained the tides, the planets, the behavior of light, the invention of the electric motor, and the existence of radio, combined to produce a flatly false statement about the most common object in the universe. Not a subtle discrepancy at the fourth decimal place. A prediction wrong by a factor of roughly 10 to the power of 30. Rutherford himself was notably relaxed about it. His concern was the experiment, and the experiment was unambiguous. What the electrons were doing out there he left to others, and in his correspondence he treated the stability problem as somebody else's difficulty. That somebody turned out to be a young Danish theorist who arrived in his laboratory the following year, and who, within about 18 months, would produce an answer that was simultaneously the most successful and the least justified proposal in the history of atomic physics. There was a second failure alongside the first, and it was almost as damning. As the electron spiraled inward, its orbit would get smaller and it would circle faster, and since the frequency of the radiation it emits is tied to how fast it circles, the light coming off it would sweep continuously upward in frequency. A dying atom would emit a smooth smear of color, sliding from red through the spectrum and out the other side, and then go dark. That is not what atoms do. Heat hydrogen gas, and it does not glow with a smooth smear. It emits a handful of extremely sharp, extremely specific colors. A red line, a blue-green line, 2 violet lines, and a series marching off into the ultraviolet. Always the same lines. Always in the same places. A hydrogen atom in a laboratory in Manchester and a hydrogen atom in a nebula 10,000 light-years away emit exactly the same colors, in exactly the same positions, forever. And in 1885, a Swiss schoolteacher named Johann Balmer had found that the positions of those visible lines could be reproduced by a simple formula involving whole numbers. He had no idea why the formula worked. Nobody did. It was a piece of arithmetic that fit the data perfectly and explained nothing, sitting in the literature for nearly 30 years like a locked box. So by 1912, the situation was this. Atoms had a nucleus. Atoms should collapse in 16 picoseconds, and did not. Atoms should emit a continuous smear of light, and instead emitted a small set of razor-sharp lines whose positions obeyed a mysterious formula built out of whole numbers. 3 separate, apparently unrelated failures. They were not unrelated. They were 3 views of a single missing idea. And the first person to grab hold of a piece of that idea did it by simply refusing to let the collapse happen, by writing down a rule that forbade it, without any justification whatsoever, and then discovering that the rule explained the colors too. His name is already in this story. The number I gave you at the very start, 5.29, is named after him. Part 4. The rule that worked and explained nothing. Niels Bohr was 27 years old when he arrived in Manchester to work with Rutherford, and within about a year he had done something that ought to be described honestly, because the honest description is more interesting than the polished one. He did not solve the stability problem. He declared it solved, and then checked what followed. His move was this. There is a quantity in orbital mechanics called angular momentum, roughly how much rotational motion a circling body carries, obtained by multiplying its mass by its speed by the radius of its circle. In classical physics, angular momentum can take any value at all. You can have an orbit with any amount of it, continuously adjustable, like a dial. Bohr replaced the dial with a switch. He proposed that the electron's angular momentum could only take certain specific values, one particular basic unit, or exactly 2 of them, or exactly 3, and nothing in between. The basic unit he chose was Planck's constant divided by 2 pi, a quantity that physicists now write as h bar, and that had turned up a decade earlier in Max Planck's work on heat radiation for reasons that had nothing to do with atoms. And then he added, with no argument at all, that while the electron sits in one of these permitted orbits, it simply does not radiate. It does not obey the Larmor formula. The spiral does not happen. Why not? No reason. It just does not. That is the entire content of the model. 1 quantization rule and 1 prohibition, neither of them derived from anything. And then the consequences came pouring out, and they were all correct. If the angular momentum can only take those discrete values, then the radius of the orbit can only take certain discrete values too. Work them out, and the smallest permitted orbit, the one with a single unit of angular momentum, the ground state, comes out to 5.29 times 10 to the minus 11 meters. Exactly the number we measure. It emerged from the algebra as a combination of 4 constants. The strength of the electric force, Planck's constant, the electron's mass, and the electron's charge. Nothing was fitted, nothing was tuned. The number simply appeared. That is the Bohr radius, and that is why it carries his name. The energies came out too. The electron, in the lowest orbit, turns out to have a total energy of minus 13.6 electron volts. An electron volt is a unit of energy convenient at atomic scale. 13.6 of them is, among other things, exactly the energy you have to supply to rip the electron off a hydrogen atom entirely, a quantity that had been measured and was sitting in the tables. And the higher orbits have energies of minus 13.6 divided by 4, minus 13.6 divided by 9, minus 13.6 divided by 16, marching upward towards 0 in a pattern set by the squares of the whole numbers. And then the colors. If an electron drops from one permitted orbit to a lower one, it must shed the difference in energy, and it does so by emitting a single package of light, whose color is fixed by that energy difference. Since the energies are discrete, the differences are discrete, so the colors are discrete. Calculate them, and out comes Balmer's formula, the school teacher's mysterious arithmetic from 1885, now derived, with the whole numbers in it, revealed as the labels on the orbits. 27 years of unexplained spectroscopy, resolved in one paper. Bohr received the Nobel Prize for it in 1922, and he deserved it. Now let me tell you what is wrong with it, because everything that is wrong with it is the reason this video exists. It does not explain anything. It restates the mystery in a more compact form. Why can the angular momentum only take those values? No answer. Why does an accelerating charge, which radiates in every other circumstance in the universe, decline to radiate here? No answer. The model does not remove the collapse problem. It makes the collapse illegal by fiat and moves on. There is a way of testing whether an idea is an explanation or a restatement, and it is to ask what else it predicts. Bohr's model, applied to helium, the very next element, with 2 electrons instead of 1, gives the wrong answer. Not slightly wrong. Wrong. It cannot handle 2 electrons at all. Apply it to any atom past hydrogen and it fails. And there is no obvious way to patch it, because there is no underlying principle to extend. You cannot generalize a decree. There is something else wrong with it that matters even more for our question tonight, and it is subtle enough that it survived in textbooks for decades. Bohr's electron travels in a circle. It has a definite position at every moment and a definite speed, and it goes around. That picture, the little solar system, the electron on a track, is wrong in the deepest possible way. In the actual ground state of hydrogen, the state we are trying to explain the size of, the electron's orbital angular momentum is exactly 0. Not small, 0. The electron in the lowest state of hydrogen does not go around the proton at all. There is no orbit. There is no circling. The one feature that Bohr's entire model was built on, the orbit and its quantized angular momentum, is not a feature of the real ground state. He got the right radius and the right energy from a picture whose central object does not exist. That is a very strange kind of success. It happens more often in physics than people admit, and it is worth naming. A model can be correct about its outputs and wrong about its contents. Bohr's model is a machine that produces true numbers by a false mechanism, and the field spent the next 13 years trying to work out which parts of it to keep. The answer, when it came, kept almost none of it. It kept the discreteness, and it kept h-bar, and it threw out the orbits, the tracks, the circles, and the picture of an electron as a small object at a location. What replaced them arrived in 1926 and 1927 from 2 directions at once, and one of those directions gives us, with no orbits, no angular momentum, and almost no arithmetic, the size of the atom. It comes from a principle you have heard of, and I would guess that what you have heard about it is not quite what it says. Part 5. What Heisenberg actually said. The uncertainty principle is probably the most famous statement in 20th century physics, and it is also the one most reliably misremembered. The version that circulates goes something like this. You cannot measure a particle's position and its speed at the same time, because in order to see where something is, you have to bounce light off it, and bouncing light off it kicks it and changes its speed. Measurement disturbs. Observation interferes. The universe is shy. That version is not entirely useless. Werner Heisenberg himself introduced the idea partly through a thought experiment about a microscope, and the microscope story does contain something real, but it points at the wrong thing, and if you keep it, the rest of tonight will not make sense, because we are about to use the uncertainty principle to explain something about an atom that nobody is looking at. Here is what the principle actually says. A quantum object does not possess a sharp position and a sharp momentum simultaneously. Not, we cannot find out both. Not, our instruments are too clumsy. It does not have them. The two quantities are not independent properties that happen to be hard to catch together. They are two descriptions of the same wave, and sharpening one necessarily blurs the other, as a matter of mathematics, whether or not anyone is in the room. I want to make this concrete with something you can actually feel, because it is not an abstract claim at all. It is a fact about waves that anyone who has ever worked with sound already knows in their hands. Imagine a single musical note, a perfect, pure tone, one frequency, no overtones, held steady. Let it run. Now let it keep running. Let it have been running forever, and let it continue forever, with no beginning and no end. That is what a perfectly pure pitch requires. Not almost forever. Forever, because the pitch of a sound is a statement about how the wave repeats, and to specify a repetition rate with absolute precision, you need infinitely many repetitions to measure it across. A tone that lasts 1 second is not a single frequency. It is a narrow band of frequencies, slightly smeared, because the fact that it started and stopped is itself information that has to be encoded in the wave, and the only way to encode it is with a spread of pitches. Now ask about that infinite pure tone. At what moment does it happen? It has no moment. It is everywhere in time. You cannot point to when it is. Perfect pitch has bought itself total ignorance of location in time. Now go the other way. Imagine an infinitely sharp click, a single instant, a spike, nothing before, nothing after. It has a perfectly definite position in time. You can say exactly when it happened, to any precision you like. What is its pitch? It does not have one. A click contains every frequency at once, in equal measure. That is why a hand clap is used to test the acoustics of a concert hall. It is not a sound with a pitch. It is a sound with all of them. And the room's response to all of them at once tells you everything. Perfect location in time has bought itself total ignorance of pitch. And between those extremes is everything real. A note that lasts 1/10 of a second has a fairly well-defined pitch and a fairly well-defined moment. And if you want to sharpen either one, you must blur the other. There is no trick, no better microphone, no more careful listening that escapes this. It is not a limitation of measurement. It is what a wave is. You can hear this in a room. A short percussive sound, a clap, a snare hit, has no pitch you can name, and its spectrum is a broad smear across the frequency range. A long sustained cello note has a pitch you can name to within a fraction of a semitone, and its spectrum is a narrow spike. The physics of the two is not different. It is the same relationship, viewed from two ends. And every audio engineer who has ever tried to isolate a very short sound and analyze its frequency content has run directly into the wall we are describing. They do not call it the uncertainty principle. They call it the time-frequency trade-off, and they know it cannot be beaten, because it is not a defect in the analysis software. There is something clarifying about that. The most famous strangeness in quantum mechanics is, in its mathematical content, an entirely ordinary fact about waves that was thoroughly understood by Joseph Fourier in the 1820s, a century before anyone was arguing about electrons. Fourier was working on heat conduction. He had no interest in atoms, but he established that any function can be decomposed into pure frequencies, and that the narrower the function in one domain, the broader its decomposition in the other, and that relationship has never needed revising. That trade is the uncertainty principle, every word of it. The only additional thing quantum mechanics adds, and it is a colossal addition, but it is a single one, is a dictionary entry. In quantum mechanics, matter is described by a wave, and in that dictionary, position corresponds to location, exactly as in the sound example, while momentum corresponds to pitch. Momentum is how fast the matter wave ripples in space, in the same way that pitch is how fast a sound wave ripples in time. So the trade transfers over, unchanged. A particle with a sharply defined position is a spike, and a spike contains every wavelength, which means every momentum. A particle with a sharply defined momentum is a pure endless ripple, and an endless ripple is nowhere in particular. Everything real sits in between, and sharpening one blurs the other. Written down, the relation is beautifully compact. Take the uncertainty in position, call it the spread in where the particle is, and multiply it by the uncertainty in momentum, the spread in how fast it is going. That product cannot be smaller than a certain fixed amount, and the amount is h bar, Planck's constant, divided by 2 pi, the same quantity Bohr had reached for 13 years earlier without knowing why. Position spread times momentum spread is at least h bar. That is the whole principle. Notice what it does not mention. It does not mention measurement. It does not mention observers, or apparatus, or light, or disturbance. It is a statement about the state of the particle, and it holds for a particle sitting undisturbed in the dark, inside a hydrogen atom, in a gas cloud, a billion light years from the nearest scientist. This matters enormously for what we are about to do, because we are about to apply it to an atom that nobody is measuring, and if the principle were really about disturbance from measurement, that application would be nonsense. Heisenberg, to his credit, moved away from the disturbance reading himself. The modern treatment separates the two ideas entirely. There is a genuine, separate mathematical statement about how much a measurement disturbs a system, worked out in detail by Masanao Ozawa in 2003, and tested experimentally by Lee Rosima and colleagues in 2012. And it is a different relation with a different form. The uncertainty principle proper is not about that at all. It is about what a quantum state can be. So here is where we stand. We have an atom that should collapse, and we have a principle telling us that a particle cannot simultaneously have a sharp position and a sharp momentum. Those two facts do not obviously have anything to do with each other. One is about electric attraction. The other is about waves. There is no visible bridge between them. The bridge is one sentence long, and it is the most important sentence in this video. If the electron falls into the proton, its position becomes sharply defined, and a sharply defined position is expensive. Part 6. The price of being somewhere. Let us make that sentence into an argument. It takes 4 steps, and none of them require anything beyond what we have already said. Step 1. Suppose the atom has some size. Call it A. We do not know what A is yet. Finding it is the whole point. All we assume is that the electron is somewhere inside the atom, and that we are completely confident about that. Well, if the electron is definitely inside a region of size A, and we know nothing more than that, then our ignorance about its position is about the size of the region. The uncertainty in position is roughly A. That is the entire content of step 1. The atom's size is the electron's positional spread. If the atom is small, the electron is confined. If the atom is large, the electron is loose. Step 2. Apply the principle. Position spread times momentum spread is at least h bar. We have just said the position spread is about a, so the momentum spread must be at least h bar divided by a. A smaller atom forces a larger spread in momentum. There is no escape clause. This is not a statement about what we know, it is a statement about what the electron's state can be. Step 3, which is the one that requires a moment's thought. We have a spread in momentum. What we want is the actual momentum, so that we can talk about kinetic energy. How do we get from one to the other? Here is the reasoning. The electron in a hydrogen atom is bound. It is not going anywhere on average. It is not drifting off to the left. So the average momentum is zero, as much of it points one way as the other. But if the average is zero, and the spread is h bar over a, then the typical magnitude of the momentum has to be about h bar over a as well. Think of it as a vector of some length pointing in an unknown direction. Its components range from plus that length to minus that length, and the spread in any one component is comparable to the length itself. So the typical momentum of the electron is about h bar divided by a. And there it is. The confinement has produced motion. Not motion in any direction in particular, not orbital motion, not circling, but a magnitude of momentum, forced into existence by nothing except the smallness of the box. Step 4. Momentum means kinetic energy. The relationship is the one from ordinary mechanics. Kinetic energy is momentum squared divided by twice the mass. Substitute the momentum we just found, and the kinetic energy of the electron comes out as h bar squared divided by twice the electron mass divided by the size of the atom squared. Read what that says. The kinetic energy of the confined electron goes as 1 over the size squared, halve the size of the atom, and the kinetic energy goes up by a factor of 4. Reduce the size by a factor of 10, and the kinetic energy goes up by a factor of 100. And this energy is positive. It is a cost. It is energy the system must possess in order to be that small. That is the counterweight we were looking for, and it satisfies every requirement we listed. It pushes outward, in the sense that it makes small configurations expensive. It is always on, because it is not a force applied by anything but a property of what it means to be confined. And crucially, this is the part that will turn out to decide everything. It gets stronger, faster, as the atom gets smaller. I want to slow down here and make sure this is felt rather than just followed, because it is the strangest idea in the whole subject, and it is very easy to nod at without absorbing. There is no force here. Nothing is pushing the electron outward. There is no repulsion, no pressure, no spring, no mechanism, no exchange of anything. The electron is not being held away from the proton by something acting on it. What is happening is that a small atom is a high-energy configuration, and it is high energy for a reason that has nothing to do with forces at all, because a confined wave must ripple rapidly, and rapid rippling is what momentum is, and momentum is what energy is made of. Squeeze the atom, and the electron speeds up, not because you pushed it, because there is no such thing as a slow electron in a small box. There is a simpler system where you can see this cost without any of the atomic complications, and it is worth 30 seconds because it strips the idea to the bone. Take a particle and put it in a box with hard walls. No attraction, no funnel, nothing but the walls. The wave has to fit inside the box and vanish at both ends, exactly like a guitar string clamped at both ends. The longest wave that fits is the one with a single arch spanning the box. Now shrink the box. The single arch has to compress. A compressed wave has a shorter wavelength. And a shorter wavelength, by de Broglie's relation, means a higher momentum, and therefore a higher energy. There is no lowest state with zero energy. The particle cannot sit still, because a motionless particle would be a wave with infinite wavelength, and an infinite wavelength does not fit in a finite box. That leftover energy has a name: zero-point energy. It is the energy a quantum system retains, even when you have taken away everything you possibly can, cooled it as far as it will go, and left it alone. It is not thermal. You cannot remove it. And it is the same quantity we are about to charge the atom for. Here, let me put your hands on it. Take a hydrogen atom, at whatever size it happens to be, and put your palms on either side of it. Now press. Gently at first. As the walls come in, something changes inside. The electron, which was spread across the whole interior, has less room, and with less room, the slow states are no longer available to it. A slow electron is a long, lazy wave, and a long wave does not fit in a small container any more than a bass note fits in a thimble. So as your hands come together, the only states left are faster ones. The electron speeds up. You did not accelerate it. You did not give it a shove. You removed its option to be slow. Press further. At half the original size, the electron carries 4 times the kinetic energy. And what have you gained for that? The attraction has improved too. The proton and the electron are closer, so the potential energy has gone down, but only by a factor of 2. You paid 4, and you were paid 2. Press further still. At 1/10 of the original size, the kinetic energy is 100 times what it was. The attraction has improved tenfold. You paid 100 and were paid 10. Keep going and it gets worse without limit. At 100th of the size, you pay 10,000 and are paid 100. Your hands are not being pushed by anything. They are simply, at every step inward, being asked for more than the arrangement is willing to give. And somewhere on the way in, without any warning or any wall, the price of the next millimeter exceeds what is on offer, and your hands stop. They stop at a specific distance, and that distance is the size of the atom, and it is the size of the sheet of paper, and the fingernail, and the hand doing the pressing. Now let us find out where it is. Part 7, 1 and 2. We now have 2 energies, and they are pulling in opposite directions. The potential energy is negative, because the charges attract, and its size grows as 1 over the separation. Shrink the atom by a factor of 10, and the potential energy becomes 10 times more negative. It rewards smallness. The kinetic energy is positive, because confinement forces motion, and it grows as 1 over the separation squared. Shrink the atom by a factor of 10, and it becomes 100 times larger. It punishes smallness. The total energy of the atom is the sum of the 2, and the entire question of what determines the size of atoms comes down to a single feature of those 2 expressions, which I want to state as plainly as I possibly can. One of them has an exponent of 1, the other has an exponent of 2. That is it. That is the mechanism. Everything else tonight is decoration on that fact. Let me show you why it decides the matter. Draw the 2 curves on the same axes, with the size of the atom running along the bottom and energy going up and down. Start far out on the right, at large sizes. Out here, the potential energy is a shallow negative. The charges are so far apart that they barely feel one another. And the kinetic energy is even smaller, because the electron has an enormous amount of room and its confinement costs almost nothing. Both terms are close to 0, with the negative 1 slightly ahead. So the total energy is slightly below 0, and drifting downward as we move left. Move left. The atom shrinks. Both curves grow in magnitude. The potential dives further negative. The kinetic climbs, but they are not climbing at the same rate. The kinetic term, with its exponent of 2, is doubling its growth rate relative to the potential at every stage. For a while, the potential stays ahead. The total energy keeps falling. This is the region where shrinking is still a good deal. And then the 2 rates cross. The kinetic term overtakes. The total energy stops falling, flattens, and begins to rise. Keep moving left, and it rises steeply, then violently, running off toward positive infinity as the size approaches zero. The funnel, in other words, has been given a floor. Not by filling it in, the funnel is still there, still bottomless, still diving toward negative infinity exactly as it did before. Nothing has repaired it. What has happened is that a second curve has been laid over it, one that rises faster than the funnel falls, and their sum has a minimum in it that neither of them has alone. That minimum is the atom. Now watch what happens if you change the exponents, because this is the fastest way to feel how narrow the escape was. Suppose the kinetic energy also went as 1 over the size, instead of 1 over the size squared. Then both curves would have the same shape, and you would simply be comparing the coefficients. If the negative one were bigger, the total would run to negative infinity, and the atom would collapse. If the positive one were bigger, the total would run to positive infinity, and the electron would fly away, unbound, and there would be no atom at all. And the case in between, exactly equal, would give you a flat line, an atom with no preferred size whatsoever, equally happy at any radius, drifting. None of those three outcomes is a universe with chemistry in it. Two of them have no matter at all, and the third has matter with no definite size, which is to say no solids, no shapes, no structure, no you. Or suppose the kinetic term went as 1 over the size cubed instead. Then there would still be a minimum, the argument still works, but it would sit at a different place, and the atom would be a different size, and every dimension of every object in the universe would change accordingly. So it is not merely that the exponents differ, it is that they differ by precisely 1, and that difference of 1 is what places the minimum where it is. The size of everything you have ever touched is a consequence of the gap between a 1 and a 2. And where do those exponents come from? This is worth saying, because it makes the result feel less like a coincidence and more like a structure. The one comes from geometry, the inverse square force law between charges, integrated to get energy, gives an energy that goes as 1 over distance, and the inverse square law itself comes from the fact that we live in 3 spatial dimensions, and the field from a point spreads over the surface of a sphere. The 2 comes from the wave nature of matter. Momentum squared appears in kinetic energy, and momentum goes as 1 over the confinement length, so the square passes through. 3 dimensions of space on one side, the relationship between energy and momentum on the other. Those 2 facts, which have no obvious connection to each other, happen to produce exponents that differ by 1, and because they do, matter has volume. I do not want to over-dramatize this, because there is a reasonable objection. Those exponents are not free parameters we could adjust. They are locked to the structure of the theory. Fair enough, but the point stands as a description of the mechanism. The reason the atom has a flaw is not that anything holds it up. It is that 2 energies with different exponents, summed, have a minimum. Take away the difference, and the flaw goes away, and matter goes with it. There is one more feature of this picture worth pointing out before we do the arithmetic, and it is the answer to a question you may already be forming. What about the other direction? What stops the atom from being enormous? Look at the right-hand side of the graph again. Out there, both curves flatten towards 0, and the total energy approaches 0 from below. 0 energy means unbound. It means the electron and proton have effectively parted company, so a very large atom is not stable either. It is just barely bound, and it is on a gentle downhill slope, back toward the minimum. The attraction pulls it in. The atom is squeezed from outside by electrostatics, and held open from inside by quantum mechanics, and it settles at the one radius where the 2 accounts balance. That radius has a value. Let us extract it. Part 8. The number that falls out. Finding the minimum of a curve is one of the oldest tricks in mathematics, and it is exactly as intuitive as it sounds. At the bottom of a valley, the ground is level. If you are standing anywhere on a slope, the ground tilts, and you are not at the bottom. So to find the bottom, Find the place where the tilt is 0. In the language of calculus, the tilt is the derivative. So we take our total energy, the positive term that goes as 1 over the size squared, plus the negative term that goes as minus 1 over the size, and we ask how it changes as the size changes, and we set that rate of change to 0. The first term, differentiated, gives minus h bar squared over the electron mass times the size cubed. The second term gives plus the charge factor over the size squared. Set the sum to 0, which is to say, set the two against each other, and rearrange. Everything with a size in it collects on one side. What comes out is this. The size at which the energy is minimized equals 4 pi epsilon naught times h bar squared, divided by the electron mass times the charge squared. 4 constants. That is all that is in it. The permittivity of free space, which encodes how strong electric attraction is. Planck's constant, which encodes how quantum the world is. The mass of the electron, the charge of the electron. No fitting, no experimental input about atoms, no spectroscopy, nothing about hydrogen specifically at all. Just 4 numbers that were already known for entirely unrelated reasons, combined in the only way that produces a length. Put the numbers in. 5.29 times 10 to the minus 11 meters. That is the number I gave you at the beginning of tonight, the one I asked you to hold on to. It is the measured radius of a hydrogen atom, and it has now arrived out of an argument that never mentioned hydrogen, never mentioned orbits, never mentioned spectroscopy, and never mentioned any measurement of an atom. And we can go one step further, because now that we know where the minimum is, we can ask how deep it is. Take that size and substitute it back into the energy expression, and out comes the value at the bottom of the valley, minus 13.6 electron volts, which is exactly the binding energy of hydrogen. It is the energy you must supply to tear the electron off. It is a quantity that had been sitting in laboratory tables since the 1890s, measured by people who had no theory of what it meant, and here it is, falling out of 2 lines of algebra about the cost of confinement. I want to let that sit for a moment before I complicate it. We used nothing but the law of electrostatics, which was known in the 1780s, and the uncertainty principle, which is 1 line. We assumed the electron was inside the atom. We asked what size costs the least energy, and out came the size of every object in the room you are sitting in, correct to 3 significant figures, along with the energy that holds it together, correct to 3 significant figures. There is a version of tonight where I stop here and let that be triumphant. But I am not going to do that, because the honest version is more interesting, and because you deserve to know what this argument actually is. It is a fortunate coincidence that the answer is exact. Let me tell you where the luck is. We made 3 approximations, and every one of them was generous. First, the uncertainty principle does not say that position spread times momentum spread equals h bar. It says the product is greater than or equal to h bar over 2. We used equality, and we dropped the factor of 2. That is a choice, and it could easily have thrown the answer off by a factor of 2 or 4. Second, we said the uncertainty in position is equal to the size of the atom. But that is a definition we invented. Is it the radius? The diameter? The standard deviation of some distribution we had not yet specified. We were vague, deliberately, and the vagueness hides a factor of unknown size. Third, we said the spread in momentum is comparable to the momentum itself. Comparable. That word is doing real work, and it is not a number. Stack those 3 together, and the honest expectation is that this argument should get you into the right neighborhood, the right power of 10, maybe within a factor of a few. That is what heuristic arguments are for. Instead, it lands on the exact value, all 3 significant figures, and it does so because the 3 sloppy factors happen to cancel. That is luck, not fraud, not circular reasoning. The derivation is genuinely independent of the answer, but luck. And I think the temptation is to be slightly disappointed by that. And I want to argue the opposite, because look at what is not luck. Not luck, that there is a minimum at all. That comes from the exponents, and the exponents are structural. Not luck, that the minimum sits at a length built from those four constants and no others. Dimensional analysis alone guarantees it. There is essentially only one way to combine the permittivity, Planck's constant, the electron mass, and the electron charge to produce something with the units of length, and any correct theory has to land on that combination times some pure number. Not luck, that the energy at the minimum is what it is, given the length. The luck is confined entirely to the pure number out front, the factor that could have been a half or a 2 or a pi, and turned out to be 1. So the mechanism is right, and the decimal places are a gift. And there is something worth noticing in that, which is not really about atoms at all. Physics is not a machine that emits truth. It is a practice of building arguments that are rougher than they look, testing them against a world that is under no obligation to cooperate, and occasionally discovering that a rough argument was pointing at something exactly real. The uncertainty estimate of the atomic radius is one of the great examples of that. It is a sketch, and the sketch is dimensionally, structurally, and numerically correct, and no one fully knows why the last of those three should be true. The proper treatment, the one with no hand-waving, no comparable, no approximately, exists. It was written down in 1926. It involves solving a differential equation, and it produces the same two numbers with no luck required. It also, on the way, appears to say something completely insane about where the electron is. And that is where we are going next. Part 9. Standing back from the machine. Before we go into the deeper water, let us stop for a moment and put the pieces we have on the table together, side by side, so that the shape of the thing is clear. We started with an object that has a size, a hydrogen atom, 5.29 times 10 to the minus 11 meters across, and every other atom in the periodic table, within a factor of a few of it. We found that the size should not exist. Electrostatics gives a funnel with no bottom, a potential energy that runs to negative infinity as the separation shrinks, and systems seek low energy, so the electron should fall in. Rutherford's nucleus made the geometry concrete in 1911 and made the problem urgent, and classical electrodynamics made it worse, because an accelerating charge radiates, and the spiral in time works out to about 16 picoseconds. The best physics in the world predicted that matter had a lifespan roughly equal to the time light takes to cross a fingernail. We found that Bohr, in 1913, made the problem go away by declaring it away, and that the declaration produced every correct number in hydrogen and no understanding whatsoever. We found that the understanding, when it arrived, came from a completely different quarter, from a fact about waves that has nothing to do with electricity. A wave cannot be sharply located and sharply pitched at once. Translate that into matter, where location is position and pitch is momentum, and you have the uncertainty principle. Position spread times momentum spread is at least h bar, always, measured or not. And then we found the bridge, which is one sentence. Confining the electron sharpens its position, which broadens its momentum, which raises its kinetic energy. Being small costs energy. A small atom is not forbidden. It is expensive. And then the mechanism. The attraction rewards smallness, with an energy that goes as 1 over the size. The confinement punishes smallness, with an energy that goes as 1 over the size squared. Because those two exponents differ, their sum has a minimum, and the minimum is at a specific, finite, non-zero radius. Not a wall, not a force. A price at which the transaction stops being worth it. And then the arithmetic, which set the price. 4 constants: the strength of electricity, Planck's constant, the electron's mass, the electron's charge, combine in the only way that makes a length, and the length is 5.29 times 10 to the minus 11 meters. Substitute back, and the depth of the valley is minus 13.6 electron volts. That is where we are. And I want to be clear that this is a real answer. If someone asks you tonight what determines the size of atoms, you can already say something true and specific. A balance between the energy released by electrical attraction and the energy demanded by quantum confinement, settling at the radius where the sum is lowest. But it is not the whole answer, and there are 3 separate holes in it that we are now going to walk into deliberately. The first hole is the one I just admitted. The argument is a sketch. Its precision is a coincidence. There is a rigorous version, and we have not done it, and until we do not actually know whether the sketch is describing the real mechanism or merely mimicking it. The second hole is that everything we have said applies to hydrogen. 1 proton, 1 electron. The simplest system there is. The periodic table has 118 entries, and almost all of them have more than 1 electron, and we have said nothing about them. And you will recall from the very first minutes tonight that the strangest fact of all was not that hydrogen has a size, it was that uranium, with 92 electrons, has roughly the same size. Nothing in the argument so far explains that. Nothing in the argument so far even begins to. The third hole is the biggest, and it will not be visible until near the end. Our answer is built from 4 constants, and we treated all 4 as given. Where do they come from? Why is the electron's mass what it is? Why is the electric force as strong as it is and not stronger? When we finally write the answer in its most compact form, all 4 constants will collapse into a single dimensionless number, a pure number, no units, roughly 1 over 137, and that number will turn out to be one of the deepest unexplained facts in physics. The size of the atom is set by it. Nobody knows why it has the value it does. It is worth naming, as well, what has quietly happened to the original question along the way, because it is a pattern that recurs all through modern physics. We began by asking why the electron does not fall into the nucleus. That is a mechanical question. It presumes a small object at a location, moving or not moving, and it asks what stops the motion. The answer we have arrived at does not address that question at all. It replaces it. There is no motion to stop. There is a configuration with an energy, and configurations with lower energies are preferred, and the preferred configuration happens to be one of finite extent. That is a different kind of explanation from the one the question invited, and it is worth noticing the substitution rather than letting it happen invisibly. Physics does this often. The answer arrives in a language the question was not asked in. Why does an apple fall? Because a force pulls it, said Newton. Because it follows the straightest available path through curved spacetime, said Einstein. And the second answer does not so much correct the first as decline to accept its framing. We are in the middle of the same maneuver here, and by the end of tonight, the framing will have been replaced entirely. So there is a long way to go. The immediate task is the rigorous version, and I should tell you now that it is going to get worse before it gets better. The proper quantum mechanical treatment of the hydrogen atom is one of the crown jewels of 20th century physics. It is exactly solvable, it is beautiful, and it reproduces every number in the spectrum. And on the way to producing those numbers, it will appear to tell us, in the plainest possible terms, that the electron is most likely to be found sitting exactly on top of the proton. The collapse, in other words, is going to come back, in the theory that was supposed to prevent it. Settle in. This next part is where the ground moves. Part 10. The Wave and the False Catastrophe. In 1926, Erwin Schrödinger wrote down an equation. It is probably the second most famous equation in physics, and unlike the most famous one, it is not something you can put on a shirt, because it is a differential equation, and it does not fit on a shirt. What it does is not mysterious though, and I want to describe it without any symbols at all, because the concept is clean. Matter is a wave. That was Louis de Broglie's proposal from 1924, and it turned out to be right. Everything with mass has a wave associated with it. You, the chair, the electron. For large things, the wave is so absurdly compressed that it never shows itself. For an electron in an atom, it is the whole story. Schrödinger's equation is the equation that tells you the shape of that wave. You feed it the landscape the particle finds itself in, the potential energy, in our case, the Coulomb funnel, and it hands you back the shapes of wave the particle is permitted to have in that landscape, along with the energy associated with each one. That is really all it is. It is a rule for finding the standing waves in a given container, in the same sense that there is a rule for finding the standing waves on a guitar string. Pluck a string of a given length, and only certain shapes survive. The fundamental, with a single arch, the first harmonic, with two, the second with three. You cannot get a shape with two and a third arches, because it would not fit. It would have to be moving at the ends where the string is nailed down. The permitted shapes are not chosen by anyone. They fall out of the geometry. Schrödinger's equation does the same job for a particle in a potential, and the fact that the permitted shapes are discrete, that there is a fundamental and then a first harmonic and nothing in between, is where quantization comes from. Bohr's mysterious whole numbers were harmonics all along. He had guessed the answer to a wave problem without knowing there was a wave. The shape the equation gives you is called the wave function, written with the Greek letter psi, and it is important to say immediately what it is not. It is not the density of the electron smeared out like butter. It is not directly observable. You cannot measure psi. What you can do is square it. Take the wave function, multiply it by its own complex conjugate, which for our purposes tonight just means square its magnitude. And what you get is a physical, measurable thing, the probability density. It tells you the probability, per unit volume, of finding the electron at a given place. Hydrogen is one of the very few realistic systems where this equation can be solved exactly, on paper, in closed form. Almost everything else in physics requires approximation or a computer. Hydrogen submits. This is a large part of why hydrogen occupies the position it does in physics education and in physics history. It is the one place where the machinery can be run all the way to the end by hand. So run it. Put in the Coulomb potential, negative, going as 1 over the distance. Solve. And the lowest energy solution, the ground state, comes out as something startlingly simple. The wave function of the hydrogen ground state is a decaying exponential. It is largest at the center, and it falls off smoothly with distance, forever, never quite reaching zero. There is no ring, no shell, no orbit, no structure. It is a single smooth mound centered on the proton. 3 things about it deserve attention. First, it depends only on the distance from the proton, and not at all on the direction. It is perfectly spherical, which means, and I want to be blunt about this because it undoes a picture almost everyone carries, the electron in ground state hydrogen is not going around anything. Its orbital angular momentum is precisely 0. There is no circulation. The little planetary diagram, with the electron on its track, describes nothing that exists. Second, look at what sets the rate of the decay. An exponential decays over some characteristic length, and in this solution, that length is, and I hope you feel this, 5.29 times 10 to the minus 11 meters. The Bohr radius appears inside the wave function itself as the scale over which the electron's presence fades. It is not something we imposed. It emerged from the differential equation as the natural length of the problem. Third, there is a constant out front, chosen so that the total probability of finding the electron somewhere, anywhere at all in the universe, comes out to exactly 1. That is called normalization, and it is the mathematical statement of an obvious physical fact. The electron does exist, and it is somewhere. Now square it and get the probability density. and look at where that density is largest. It is largest at 0, at the exact center, at the proton. Take a moment with this, because if you follow the words as they are usually stated, quantum mechanics has just said something appalling. The probability density is a maximum at the nucleus. The most likely place to find the electron is at the center of the atom, on top of the proton, which is precisely the thing we spent the last hour explaining could not happen. The funnel has reappeared, in the theory that was supposed to have solved it. The whole edifice, de Broglie's waves, Schrödinger's equation, the exact solution, has apparently reproduced the classical catastrophe with extra steps. The electron falls in after all. And here is the awkward part. The mathematics is not wrong. The probability density really is maximized at the origin. That is not a mistake in the solution, or an artifact of the method, or something that goes away with a better calculation. It is a true statement about the hydrogen ground state, and it will still be true when we are finished. So either quantum mechanics predicts atomic collapse, which it manifestly does not, since it also predicts the correct energy levels and every spectral line in the observed universe, or we have misread what we are looking at. We have misread what we are looking at, and the misreading is so ordinary, so easy, and so instructive that it is worth the whole detour. The error is in 5 words that we glided straight past. Probability per unit volume. Part 11. There is almost no room at the center. Probability per unit volume is a rate, not a total. It tells you how concentrated the probability is at a location, not how much probability there is at that location. To get an actual probability, you have to multiply the rate by an amount of space. That distinction is not exotic. It is the difference between population density and population. The most densely populated place in a country might be a single city block, but the number of people who live on that block is small, because it is one block. If you ask which distance from the city center the largest number of people live at, you are asking a different question from which distance has the highest density, because the amount of land available at a given distance from the center grows as you move out, and eventually, the growing area outruns the thinning density. That is exactly our situation, and the atom makes it sharper than any city, because we are in 3 dimensions, and the geometry is severe. Ask where the electron is likely to be found at a given distance from the proton. Because the ground state is perfectly spherical, every point at the same distance has the same probability density. Together, all those points form a thin spherical shell, like the skin of a bubble. So the question becomes, how much probability is in that shell? And that is the density at that radius multiplied by the volume of the shell. The volume of a thin spherical shell is its surface area times its thickness, and the surface area of a sphere goes as the radius squared. Now look at what happens at the center. At the center, the probability density is at its maximum, the largest it will ever be. But the radius is 0, so the surface area is 0, so the shell volume is 0, and any finite number multiplied by 0 is 0. The probability of finding the electron at the exact center of the atom is 0, not small, 0, and it is 0 for a reason that has nothing whatsoever to do with physics. It is 0 because there is no room there. A sphere of 0 radius has no surface, and a shell with no surface holds nothing, no matter how enthusiastically the density piles up in it. Let me walk you out from the center, slowly, so you can feel the 2 effects trading against each other. Stand at the proton, look around. The density of electron here is as high as it gets anywhere in the atom, but the shell of space you are standing on is a point. There is nowhere to be. Whatever probability you might have had, you have nowhere to put it. 0. Take a step outward. The shell is no longer a point. It is a tiny sphere with a real, if minuscule, surface. The density has dropped very slightly. The exponential has barely begun to fade this close in. So there is now a small, but non-zero amount of electron here, more than there was. Take another step. The shell's surface has grown by the square of the distance. It is 4 times bigger when you are twice as far out. The density has faded a little more, but the growth of the shell is winning easily at this stage, because the density curve is nearly flat near the origin, while the area curve is climbing steeply from nothing. There is more electron in this shell than the last. Keep walking. The pattern continues, and it continues in your favor for a while. Every step outward, you gain more room than you lose density. The shells are getting fatter, faster than they are getting emptier. But the exponential is patient, and exponentials always win in the end. It has been fading the whole time, and now it is beginning to fade seriously. Somewhere out here the two rates come level. The room is still growing as the square of the distance, but the density is now falling faster than that. One more step, and you will have less electron in your shell than in the one behind you. Stop. Do not take that step. You are standing on the peak. You are standing at the most probable distance to find the electron in a hydrogen atom. Look at the reading. 5.2, 9 times 10 to the minus 11 meters. It is the same number. Again. I want to be precise about how remarkable that is, because it is easy to let it slide past as a tidy ending. The route we just took shares nothing with the route we took an hour ago. The heuristic argument used the uncertainty principle, an assumption about the relationship between the atomic size and the positional spread, and a minimization of energy. This route used a differential equation, an exact analytic solution, and a piece of spherical geometry. There is no uncertainty principle anywhere in this second calculation. There is no energy minimization. We were not looking for a balance point. We were looking for the peak of a probability distribution, which is a different kind of question entirely, and it is at exactly the same radius. If you want to know what it feels like when physics is working, when it is not just producing numbers, but actually describing something, that is what it feels like. Two arguments with no shared assumptions, aimed at two different questions, landing on the same address. It is worth noticing that this same confusion, in a less dramatic costume, is everywhere. Ask where the water is deepest in an ocean, and you get one answer. Ask where most of the ocean's water actually sits, and you get a different one, because the deep trenches are narrow, and the shallow shelves are vast. Ask which age has the highest death rate, and which age most deaths occur at, and the answers differ, because there are more people alive at some ages than others. In every case the trap is the same. A density has been mistaken for a total, and the amount of the thing being measured over has been quietly forgotten. In the atom, the effect is unusually severe, because the amount of space at radius r grows as the square of r, and squares grow fast. Double your distance from the nucleus, and you have 4 times as much room. Triple it, and you have 9 times. That is an enormous handicap for the center to overcome, and it does not overcome it. The exponential decay is fierce, but it starts flat, and near the origin, the geometry wins comfortably. Which is why the peak sits where it does. It is not at the point of highest density, and it is not at the point of greatest room. It is at the one radius where the product of a thing that is falling and a thing that is rising is momentarily largest. And that is a definition of a compromise, not of a boundary. You can do the peak finding formally, of course, and it takes about 3 lines. The radial probability, density times shell volume, is a rising quadratic multiplied by a falling exponential. Differentiate the product, set the result to 0, and you get 2 solutions. One is at radius 0, which is the trivial one. It is the flat bottom of the curve at the origin, where the shell volume kills everything. The other is at exactly the Bohr radius, and that is the peak. Notice, incidentally, that this also resolves the older paradox in a way the heuristic argument never quite did. We do not need to say that something prevents the electron from being at the nucleus. Nothing prevents it. There is simply nowhere at the nucleus to be. The atom does not hold the electron away from the center. The center is not a place with any room in it. And notice one more thing, which will matter shortly. What we have found is a peak, the most likely distance. That is one answer to, how big is the atom? It is a good answer. It is the one everybody quotes. It is not the only one, and it is not the average. And the difference between those two is about to take away the last solid thing you were holding. Part 12. The thing with no edge. Let us do an experiment that cannot be done, in order to understand something that is true. Imagine a very large collection of hydrogen atoms, 1 million of them, all in the ground state, all identical, all undisturbed. And imagine that for each one, you can perform an idealized measurement that tells you how far the electron is from the proton at that instant. One number per atom. You cannot actually do this. But nothing in the thought experiment is unphysical, and it makes the mathematics into something you can watch. Take the radial axis and divide it into bins, a series of narrow boxes, each covering a small range of distances. Measure an atom, get a distance, drop a token in the appropriate box, measure the next, and the next. At first the boxes fill erratically, a few tokens here, a few there, no shape. After 1,000 measurements a bulge is visible. After 10,000, the bulge has smooth sides. After 1 million, the histogram has converged into a curve that you would recognize, 0 at the origin, rising to a clean peak, then falling away. The tallest box sits at the Bohr radius, exactly where the calculus said the peak would be. The theory and the tally agree. Now ask a different question of the same data. Not which box is tallest, but what is the average of all the numbers you recorded. These are not the same question, and it is worth being clear about why. The tallest box tells you the single most common outcome, what a statistician calls the mode. The average tells you where the distribution balances, what we call the mean. For a symmetric distribution, a nice, even bell, they coincide, and you can be sloppy about the difference. For an asymmetric distribution, they do not, and this one is deeply asymmetric. Look at the shape again. On the left of the peak, the curve drops to 0 within 1 Bohr radius. It has nowhere to go, because there is no such thing as a negative distance. On the right, it decays exponentially, which means it goes down and down and down, and never actually arrives at 0. There are measurements at 2 Bohr radii, and at 5, and at 10. They get rarer very fast, but they are there, and each one contributes a large number to the average. So the tail pulls the mean outward. Do the integral, and it is a standard one, a power of the distance times a decaying exponential, evaluated using a formula that turns the whole thing into a factorial, and the average radius comes out at 1.5 times the Bohr radius. 50% larger than the most probable value. So now we have two answers to the question, how big is a hydrogen atom? And they are both correct, and they disagree by half. Most probable distance, 5.29 times 10 to the minus 11 meters. Average distance, 7.9 times 10 to the minus 11 meters. And there is a phrase in this territory that I want to flag as actively misleading, because it trips up people who have studied the subject formally. The average value is called, in the technical literature, the expectation value. That name suggests it is what you should expect to measure. It is not. If you measure a single hydrogen atom, the value you are most likely to get is the Bohr radius, not the expectation value. The expectation value is what a large number of measurements average to, and for a lopsided distribution, the average is a place where relatively few of the measurements actually landed. But the real weight of this part is not the arithmetic. It is what the shape of that curve tells you about the object. There is no edge. I want to say that as plainly as I can, because almost everyone, including people who use quantum mechanics daily, carries around a mental image of an atom as a small hard sphere with a surface, a ball, a tiny marble with a boundary, so that inside is atom and outside is not atom. There is no such boundary. There is a probability distribution that is largest at one radius, has a mean at another, and decays exponentially outward, which means it never reaches zero anywhere, not at 10 Bohr radii, not at 1,000, not at any distance you care to name. Follow that honestly, and it produces a result that sounds like a joke, and is not. The wave function of every hydrogen atom in your body is non-zero at the surface of the moon. Vanishingly, unimaginably small, the probability is so far below anything meaningful that it will never manifest in the lifetime of the universe, but not zero. Mathematically, every atom in you extends, in the faintest possible sense, everywhere. So what is the size of an atom? It is a decision. You have to choose a convention. You can quote the most probable radius, which is the Bohr radius. You can quote the mean radius, which is 1.5 times that. You can quote the radius containing 90% of the probability, or 99, and get different numbers again. Chemists mostly use radii derived from how closely atoms actually pack together in real bonds, which is yet another convention and gives yet another set of values. None of these are wrong. None of them is the true edge, because there is no true edge to find. The number 5.29, which we have now derived twice by independent methods, and which is genuinely fundamental, is not the location of a surface. It is the characteristic scale of a fade. And here is the thing I would like to leave you sitting with, because it is the strangest consequence of everything we have said tonight, and it does not get said often enough. Every hard object you have ever encountered is made entirely of things that have no hardness and no edges. The table has a surface, its atoms do not. The floor has a boundary, its atoms do not. Solidity, the most reliable, most immediate, most trusted property of the physical world, the one your entire body is calibrated around, has no counterpart at the level of its own ingredients. It is not inherited from below. It is manufactured, at some intermediate scale, out of parts that do not have it. Which raises a question we have been circling all night without asking directly. If atoms have no edges, why does anything feel solid at all? Why does a hand not pass through a table made of edgeless probability clouds? The answer is not the one you were probably taught, and it is the last piece of the puzzle. Part 13. What actually determines the size of atoms? Before the last piece, let us close the loop on the calculation, because there is a beautiful convergence waiting there, and it would be a shame to leave it out. We have the wave function. That means we can compute averages of anything we like, not just distance. In particular, we can compute the average potential energy and the average kinetic energy of the electron, and compare them with the rough values our heuristic argument produced an hour ago. Start with potential energy. Take the Coulomb expression, weight it by the probability of the electron being at each distance, and integrate over all space. The integral is standard, and the result is clean. The average potential energy of the electron in ground state hydrogen is minus 27.2 electron volts. Look closely at that expression, because it says something quietly elegant. It is exactly the classical Coulomb potential energy, evaluated at the Bohr radius, not at the average distance, not at some awkward weighted compromise. At the Bohr radius exactly, the 1 over distance weighting and the shape of the distribution conspire to give precisely the value you would have got by putting the electron at the Bohr radius and forgetting quantum mechanics entirely. Now kinetic energy, which is harder, because kinetic energy is about momentum, and our wave function describes position. The bridge is a mathematical operation called a Fourier transform, and it is the same operation that connects a sound to its spectrum of pitches. Feed it the wave function in terms of position, and it hands you back the wave function in terms of momentum, the same state, described by what momenta it contains, rather than by what places it occupies. This is the formal machinery underneath the pure tone and click picture from earlier, and it is why the uncertainty principle is a theorem rather than a guess. Do that transform for hydrogen, and you get a momentum space wave function. Square it, and you have the probability density in momentum, how likely the electron is to have each possible momentum. And now something happens that ought to feel familiar, because it is the same trap in a new location. The momentum probability density is a maximum at zero momentum. Read carelessly. That says the electron is most likely to be stationary, which, if it were true, would mean no kinetic energy and no counterweight, and the atom collapsing again. It is the same error. Probability per unit volume, this time volume in momentum space. To find the likelihood of a given momentum magnitude, you must multiply by the shell in momentum space, which again goes as the square of the magnitude, which again vanishes at zero. And once again, the product peaks at a sensible, non-zero value. Push the calculation through, substitute, reduce to a standard integral, evaluate, and the average of the momentum squared comes out as h bar squared divided by the Bohr radius squared, which means the average kinetic energy is h bar squared divided by twice the electron mass divided by the Bohr radius squared. And I would like you to look at that expression very carefully, because you have seen it before. That is, character for character, the expression we wrote down in part 6 from the uncertainty principle. Not a similar expression, not the same up to a factor, the identical formula. The sloppy heuristic estimate of the kinetic energy of a confined electron is exactly the rigorous quantum mechanical average. Put in the numbers, plus 13.6 electron volts. So the ledger for a hydrogen atom in its ground state reads, average kinetic energy plus 13.6 electron volts. Average potential energy minus 27.2 electron volts. Total minus 13.6 electron volts, which is the measured binding energy, and the value the heuristic produced, and the value the Bohr model produced, and the value spectroscopy measured in the 1890s. There is one more thing hiding in those two numbers that I do not want to walk past. The potential energy is exactly minus 2 times the kinetic energy. That is not a numerical accident of hydrogen. It is a theorem, the virial theorem, and it holds for any stable system bound by an inverse square attraction. It holds for the Earth going around the Sun. It holds for stars orbiting in a galaxy. The energy accounting of the smallest bound object in nature obeys the same rule as the solar system, and the rule was written down by Rudolf Clausius in 1870, decades before anyone knew that atoms had insides. So now let us answer the question in the title, completely and plainly. What determines the size of atoms is an equilibrium, a negotiated settlement between two energies that scale differently with distance. On one side is electrostatic attraction, which rewards closeness. Its energy is negative and grows as 1 over the separation. It wants the atom small, and it never stops wanting that, at any distance, all the way down. On the other side is the energy cost of quantum confinement. Not a force, not a repulsion, a price. Localizing a wave into a small region requires that wave to ripple rapidly. Rapid rippling is momentum. Momentum is kinetic energy, and that energy grows as 1 over the separation squared. Because those two exponents differ, 1 against 2, the sum of the two has a minimum at a finite, non-zero radius. That radius is fixed by 4 constants and nothing else: the strength of electricity, Planck's constant, and the mass and charge of the electron. It comes to 5.29 times 10 to the minus 11 meters. That is the answer for hydrogen. For everything else, 2 more ingredients enter, and they are what keep the whole periodic table inside one narrow band of sizes. The first is nuclear charge, partially cancelled by screening. Add protons, and the pull on each electron strengthens, which shrinks the cloud. Helium's nucleus pulls twice as hard as hydrogen's, and a helium atom is genuinely smaller than a hydrogen atom. One of the most counterintuitive facts in chemistry, since you have doubled everything in the atom, and it has shrunk. But in neutral atoms, you must add an electron for every proton, and the inner electrons stand between the nucleus and the outer ones and blunt its pull. The outermost electron in a cesium atom, with 55 protons underneath it, feels an effective charge of only a couple of units. Adding a proton pulls in, adding an electron pushes out and screens the next. The two effects very nearly cancel, and that cancellation is why uranium is not 92 times wider than hydrogen. The second ingredient is the exclusion principle, and this is the one that answers the question I left hanging at the end of the last part. Electrons are fermions, which means no two of them can occupy the same quantum state. Not, will not, cannot. So as you add electrons, they cannot all pile into the ground state. They are forced upward and outward into successively larger shells. Within a row of the periodic table, atoms shrink from left to right as the nuclear charge climbs, and the shell stays put. Drop down to the next row, a new shell opens, and the size jumps back up. That sawtooth, repeating across the table, is why every element ends up in the same size range. And it does something more important than that. In 1967, Freeman Dyson and Andrew Leonard proved a result called the stability of matter. The uncertainty principle, on its own, keeps one atom from collapsing. It does not keep a large number of atoms from collapsing collectively into a volume far smaller than the sum of their parts. What forbids that? What guarantees that a kilogram of anything occupies about 1,000 times the volume of a gram of it, rather than something much smaller, is the exclusion principle. Dyson and Leonard proved it, with a bound so weak it was almost comic, and Elliot Lieb and Walter Thuring produced a far more elegant proof in 1975. If electrons were not fermions, if they could share states, ordinary matter would implode. The binding energy of a lump of material would grow faster than its size, and everything would collapse into something dense and small and unrecognizable. Which finally answers why your hand does not pass through the table. It is not mainly electrostatic repulsion, which is what most of us were taught. It is that pushing your hand into the table would require the electrons in your hand to enter quantum states already occupied by the electrons in the table, and the exclusion principle forbids it, and the energy cost of the alternative is enormous. What you feel as the hardness of the table is a law about the identity of electrons, transmitted directly to your fingertips. So, what determines the size of atoms? A balance between electrical attraction and the energy cost of confinement, refereed across the periodic table by screening and the exclusion principle. That is the full answer, and every piece of it is quantitative, tested, and understood, except for one number, which nobody understands at all. Part 14, 137. There is a way of writing the Bohr radius that strips away all four constants and replaces them with one. Every particle has associated with it a length called its Compton wavelength, which is roughly the scale at which its quantum nature and its relativistic nature meet. For the electron, that length is about 3.9 times 10 to the minus 13 meters. It is the electron's own intrinsic scale, as close as anything gets to the size of an electron in a subject where electrons do not have sizes, and the Bohr radius, it turns out, is simply that length divided by a pure number, divided by the fine structure constant, which is written with the Greek letter alpha, and whose value is approximately 1 over 137. So an atom is about 137 times larger than the intrinsic quantum scale of the electron sitting inside it. That factor is the entire reason atoms are the size they are, rather than 400 times smaller. The same number shows up in the energy, 13.6 electron volts, the binding energy we have now derived three ways, is 1/2 of alpha squared times the rest energy of the electron. The electron's rest energy is enormous, about 500,000 electron volts. Multiply by alpha squared, which is roughly 1 in 19,000, and you get 13.6. The strength with which atoms hold themselves together is the electron's own mass energy, discounted by that number twice over. Alpha is dimensionless. It has no units. It is not meters or kilograms or seconds. It does not depend on any human choice of scale. An alien civilization, with no shared units with us, would measure the same one over 137. It is one of a small handful of numbers that are simply a description of what kind of universe this is, and nobody knows why it has that value. Not the derivation is difficult, not it will fall out of the next theory. There is no known reason. It is measured to 12 significant figures, 1 over 137.03599, and it is an input to physics rather than an output. The standard model does not predict it, it accommodates it. Richard Feynman, who spent much of his life on the theory in which alpha is the coupling constant, wrote about it in a way that has never been improved on. He called it one of the greatest damn mysteries of physics, a magic number that comes to us with no understanding by man. He said that all good theoretical physicists put it up on their wall and worry about it. So the answer we assembled tonight is complete, and it has a hole in the middle. We can say exactly what determines the size of atoms, a balance between attraction and the cost of confinement, extended across the elements by screening and exclusion. We cannot say why that balance settles at 5.29 times 10 to the minus 11 meters rather than somewhere else, because the number that fixes it is a number the universe simply came with. Let me show you 3 places where that becomes tangible rather than philosophical. The first is the muon. A muon is an electron in every respect except one. It is 207 times heavier. Everything else, charge, spin, behavior, is identical. And our formula says the atomic radius goes as 1 over the mass. So if you build a hydrogen atom out of a muon instead of an electron, it should be 207 times smaller. It is. Muonic hydrogen has a radius of about 2.6 times 10 to the minus 13 meters, exactly as predicted. And because the muon spends so much of its time deep inside the proton's charge distribution, muonic hydrogen turned out to be an extraordinarily sensitive probe of how big the proton itself is. In 2010, Randolph Pohl and his collaborators used it to measure the proton's radius and got an answer 4% smaller than the accepted value, 7 standard deviations away, which in this business is not a discrepancy but a scandal. It was known as the proton radius puzzle, and it stood for a decade before newer measurements came down toward the muonic value and the tension largely resolved. The muon, which exists for 2/millionths of a second before decaying, had been right. The second is what happens when you give the electron more energy. The radius of an excited state goes as the square of the quantum number, and there is no limit to how high that number can go. Take a single cesium atom and start feeding energy to its outermost electron. At the 10th level, it is 100 times its ordinary size, still invisible, still ordinary, as far as anything around it is concerned. At the 100th level, it is 10,000 times its ordinary size, about half a micrometer. That single atom is now larger than most viruses. At the 500th level, it is 250,000 times its ordinary size, tens of micrometers, larger than a red blood cell, approaching the width of a human hair. States above the 1,000th level have been produced in laboratories. One atom, not a molecule, not a crystal, not a cluster. One nucleus and its electron, the same equation, the same balance, the same physics we spent tonight assembling, simply settled at a radius 250,000 times further out. You could, in principle, See it. These are called Rydberg atoms, and they are not a curiosity. Their exaggerated size makes them interact strongly across long distances, which is why they are one of the leading platforms for quantum computing. The Bohr radius, in other words, is not an edge and not a rule. It is where the ground state settles, change the terms, and the settlement moves. Which brings me to the third place, and it is the largest. The balance we have been describing does not only apply to atoms. Take a white dwarf star, the collapsed remnant of something like the Sun, a mass comparable to our star packed into a volume the size of the Earth. What holds it up against its own gravity? Not heat. White dwarfs are dying and cooling. Not nuclear burning. It has stopped. What holds up a white dwarf is electron degeneracy pressure, which is the uncertainty principle and the exclusion principle operating together on a stellar scale. Confining the electrons costs energy, and no two of them may share a state, and between them they push back against the weight of a star. It is the same argument, precisely the same argument, that gives you 5.29 times 10 to the minus 11 meters, evaluated under different conditions, gives you a star the size of a planet. And there is a point at which it fails. Push past about 1.4 times the mass of the Sun, the Chandrasekhar limit, and the electrons are forced to such high momenta that they approach the speed of light, and once they do, the pressure stops rising fast enough to keep up with the gravity. The balance breaks. The collapse we spent this whole video explaining could not happen. Happens. The star falls in on itself, the electrons are driven into the protons, and what is left is a neutron star, where the same argument runs again with different participants. Push past 2 or 3 solar masses, and it fails there too, and there is nothing left to run the argument with, and a black hole forms. So the chain is unbroken. The reason a hydrogen atom is 5.29 times 10 to the minus 11 meters wide, and the reason a star can collapse into a singularity, are the same piece of physics. The first is the balance holding. The last is the balance losing. And underneath all of it, setting the scale for the whole chain, is a number with no units and no explanation. I said at the start that the atom does not resist collapse. I want to end there, because I think it is the truest thing in tonight's material. The classical question was, why doesn't the electron fall in? And that question assumes a small object at a place which could move to another place and which something must be preventing from doing so. Every part of that assumption is wrong. There is no small object, there is no place, there is no falling, and there is nothing preventing anything. There is a wave in a well, settled into the shape that costs the least, fading outward with a characteristic scale of 5.29 times 10 to the minus 11 meters, and never quite ending anywhere. The atom did not survive the collapse. It was never the kind of thing that could collapse, because it was never the kind of thing that had a position to lose. 16 picoseconds. That was the lifespan classical physics assigned to the material universe. The time light takes to cross a fingernail. Everything that has happened since is time that physics said would not be available. Every star that formed, every planet that cooled, every one of the roughly 430 quadrillion seconds that have elapsed since the beginning, and every atom in the hand you are resting your head on, exists in the margin between what the equations predicted and what actually occurred. So what determines the size of atoms? A negotiation between an attraction with no bottom and a cost that rises faster than the attraction falls, settled at the one radius where the arithmetic balances, scaled by a number nobody can derive. And every solid thing in the universe is that settlement, repeated, without interruption, since the beginning.